And the time has now come to listen to Mr. Andrea Friso, R&D and Product Manager of the Business Unit Master Alloy at Ligor. He has a consolidated experience in the metallurgy of precious metals and jewelry production processes. Mr. Friso coordinates the testing and the release on the market of new alloys, supporting the technical sales team all over the world. He will talk about the production of jewelry in binder jet additive manufacturing, our experience with steel, silver 925 and platinum 950. His presentation is focused on the use of the binder jet technology for the production of jewelry, starting from steel, silver, platinum powders. Specifically, the results will be shared that have been achieved in the legal laboratory, starting from 3D printing systems, binder jet AM systems, showing that this technology is a realistic possibility, although it still has to be perfected, in the world of additive manufacturing for the production of jewelry.
Grazie e buongiorno a tutti. Quella di oggi vuole essere la continuazione della prima presentazione.
Thank you very much. So this is the continuation of my presentation last year, when we evaluated the binder jet technology and compared it with other existing technologies. Today we're going to speak in a more detailed way with a short overview of the process, a short video, and then we'll talk about some of the most relevant parameters of the process for the successful printing and sintering with the binder jet. We will then see the results, the present results of our studies on different materials covered during these 2 years, since we worked on different types of steel, silver 925 and platinum 950. I would like to start with a video that will quickly show you the process. It's additive manufacturing, so you start from a 3D drawing. We use file step that are downloaded through a software to allow for the appropriate sintering. The design feeds the printer that you can see here, and the powder is uploaded. So the metal powder that is used for the printing process. The build unit is brought. It is a tray containing the printing floor that goes down on the Z-axis progressively as printing takes place. This is the plate on which a roller deposits the binder contents, which are then sprayed and that are used to create planes, bidimensional growing planes on the Z-axis. This is like a 2D printer, where I have the ink on one single plane, but here we have a 3D development. The build unit is then cured. That is, the binder has to be treated to guarantee mechanical resistance. And then the pieces are extracted at the moment manually. After having been cured, they are sufficiently resistant to be manipulated. They're placed on trays and are then submitted to heat treatment to achieve the sintering process. The item is now ready to be placed in the oven. The oven is loaded with the trays, and the items will remain in this chamber, characterized by high thermal stability. So the heat cycle in every phase has a very low degree of variation in the different areas of the chamber. And this is fundamental to obtain dense, stable, and homogeneous items. So in 1 second, I've actually shown you how it works, even though I haven't told you anything about the process yet. These 3 slides simply summarize what I've just shown you. So, deposition of the powder, deposition of the binder in a selective way depending on the design of the item, where you need the structuring of the powder. Evaporation, that's a first phase to give mechanical resistance, which takes place directly in the printer. It's proprietary technology. Then the powder is cured, the item is extracted, and following sinterization, we have the cooling cycle. Let's have a look at some of the most relevant parameters in the BJT process so that we can better understand how it works conceptually. We're talking about metals, therefore we start from an alloy. The type of alloy defines the characteristics of the material. And then we have some specific parameters of the process, such as the drawing, the design, the printing, the preparation for sintering, and sintering as such. Initially, we wanted to include finishing, but that actually depends on the good success of sintering, so we do not have any specific aspects, maybe the roughness of the item immediately after sinterization, that we view as peculiar to this technology. So let's have a look at the critical parameters related to the alloy. Well, the heat characteristics of the alloy are fundamental because they define the sintering temperature. The type of alloy also defines the possibility of eutectic low melting phases that could compete with a medium low temperature phase for the elimination of the binder. In a while I will show you some examples. And then of course the reactivity of the material that defines the number of atmosphere within which I can work during the debinding and the sintering phase. Granulometry. There is a trade-off between the yield of the powder. We have perfectly controlled atomization phases, but I have to take into consideration a phase which would cost a lot if you're using precious material, and the optimum grain size, which according to the literature is very, very low in binder processes. So you need to select whenever possible an alloy that gives you a good production yield in terms of the powder, and the need, especially for jewelry and fashion, requiring a density equal or close to 1. Design and drawing. One of the most important aspects of binder jet technology is that in all intermediate phases prior to sinterization, I have an aggregate of metal powder and binder. A polymeric binder that is used in a much smaller quantity compared to other additive technologies such as MIM. Here we have approximately 1% of the weight of the material. I still have to consider the shrinkage in time due to the fact that my initial item has a certain size during the drawing and designing phase that must be bigger due to the fact that there is the binder as well. And the z-axis shows a product, an item, which is 15% larger when I'm printing it compared to the final item on the x, y plane and 17% on average on the z-axis, which is the axis on which the binder is deposited. So if the object has been perfectly sinterized, these parameters are independent of the type of alloy. So the size monitoring in terms of size prior and after sintering in steel, platinum, and silver is an independent value, at least if we consider powders that have been atomized in inert gas. This is the ideal case, so once you decide the size, I can proceed with the production. But on top of that, you have to think about the possible softening of the piece and the presence of gravity, which plays a role also during sintering. This means that if the item has not been adequately placed in the sintering oven, could be distorted by gravity, or the shrinkage in area close to parts that have a bigger mass could actually be strained in an irregular way, leading to undesired distortion. To tackle this problem, during the design phase, it is possible to produce supports. You can see on the left the green and two sintered objects in steel, which during printing have been printed just as they were, without that brick that you can see here, which is made of aluminum. The green one, in the green one, the powder supports the object while it is growing, so there is no mechanical issue here. But if I'm sintering the item, or when I'm sintering the item, unless I use a support, of course, you can place the brick also in a different way, but here it acts like a bridge. And it shows the bridge that you see in the item on the right indicates the distortion caused by gravity. So the solution could be placing this brick and consider the tolerance of the object after sintering so that the object can be supported rather than caving in, and giving me the possibility to extract the brick after sintering. In other cases, it is possible to co-produce both the item and the support. This has a meaning when we're talking about non-precious materials, but it becomes much more costly if you're using silver or other precious materials. Well, here the shrinkage phase that takes place during sintering allows me to have both the support and the item devoid of any tension that could take place when I have a base that has a certain friction and therefore prevents the upper part of the item to slide, causing tension at the base that could also lead to distortions. So these are two amongst the many tricks that allow you to obtain complex forms, bearing in mind the thermal phase of the alloy. On your left in green, you can see another support. This is for a watch box. This is AIS 1316L. And in this way, we can guarantee excellent tolerance in terms of the circular shape of the item. The very same item produced without the support showed a distortion with a tapering between the base and the upper part of the object. This is another example. Here you can see the different tolerances. We're talking about items with size base less than 8 times 8 centimeters and 7 centimeters in height. Possible tolerance range goes from 0.05 and 0.15 millimeters, depending on the geometry of the item and depending on all the other aspects. The shrinkage on the XY planes can be stabilized, allowing us to achieve items with reasonable tolerances. These are lengths of a watch bracelet. The printing phase is the most important one. We have two systems in-house, an HP printer and a desktop metal printer. They have been chosen predominantly because of the size of their printing chamber. The HP machine has a printing volume which is pretty significant, about 19 liters. We can use significant quantities of powder suitable for series production. The HP printer was also the first one we started using with steel, non-precious metals to explore the technology. When full loaded, it can contain 200 kilograms of steel. And you cannot think of processing, like we started last year, precious metals in such a big chamber. Because, of course, you have to cover it all up on the Z-axis. So we have decided to make use of another printer, which can contain about 1 liter. 10 times 4 centimeters is a printing capacity, and it allows us to work with approximately 30 kilograms of platinum powder. Two similar technologies, each one with its own peculiarities, that discriminate between the use of precious and non-precious metals. Our experience with the different printers tells us that depending on the type of material, on the granulometry, and the printer that we're using, it is necessary to have a learning curve, which is specific for that given setup. So after tests have been concluded, we can say that the printing phase is not the most complex one of the whole process, because the heat phase, the debinding and sintering phase, is much more surprising and has required many more interactions to achieve satisfactory results. The interesting aspect of the printing phase is that you compare it with XML. In binder jet, the speed of printing depends on the speed with which the head printing or the binder deposition head is moved. And this is independent, whether I have a punctiform object or whether I have hypothetically to cover the whole printing area. With XLM, the work on the layer is directly dependent on the number of pixels that I need to cover. So this is actually in favor of the binder jet print because it is much faster, at least during the printing phase. Printing time, therefore, depends on the total height of the item and not so much on the area of each slice. It is interesting to focus on the layout of the items, making use or opting for the plane of the biggest encumbrance of the item to guarantee support in terms of gravity. Items have to be placed a few millimeters one away from the other, so you can actually fill the surface quite well. Trivial as it may sound, the higher the resolution, the better for the jewelry world. With our powders, the roughness you obtain at the end of the printing process is approximately 4 microns on the XY planes. It is higher on the Z-axis, about twice as much. And this depends, of course, on the binder elimination phase. The binder. Well, the binder is a polymeric compound owned by the companies selling printers, and it guarantees the innermost adhesion of the powder particles during all low temperature phases. So it allows me to decide what is going to become an item and what is going to be reusable powder. The powder that remains in the machine is immediately ready for a second printing cycle. And the resistance of the green item depends on the quantity of binder. Hypothetically, I can also work with areas devoid of binder, because maybe they're protected by an outer shell. And the advantage is increased densification. The number one enemy of good densification is the possible presence of binder that has not been eliminated, that did not evaporate, that did not evacuate. I have to guarantee a certain mechanical resistance, therefore, mechanical strength. So for the processing phases, I have to be on the safe side, and I need to guarantee, thanks to the binder, for the whole section of the item, a minimal strength. One of the challenges we have today is that the binders that are present on the market are boiled down to one binder, in the sense that they promise to us to develop binders depending on the temperature and on the material, but the ones that work best have been optimized for high temperatures. And this leads to possible complexities for, say, copper-based materials or silver and gold materials. The curing phase, which you saw before, during which the item is introduced in a chamber after being printed, envisages an intermediate temperature between 120 and 180 for 3 to 5 hours, depending on the quantity of powder that has to be cured. And it has to bear in mind that some materials might be reactive. This is the case of silver and bronze. Therefore, the curing process for these metals, which is carried out in air, could lead to tarnishing, to oxidation. And oxidation may be detrimental to the sintering phase. I don't want to bore you too much talking about sintering. Let's just remember that this process makes use of thermal energy, so increased temperature, heat that is released into the system, so that a compound of non-aggregated powders that are kept together by the binder is transformed through adhesion between the different grains of powder. This process is called necking and starts at a much lower temperature compared to the actual melting of the material and the sintering temperature. But this is the beginning of the densification process. So there are mechanisms of surface diffusion that allow us to obtain a meniscus which spreads then in the spaces in the powder, and then as the temperatures further increase, there are some mechanisms in the powder particle that allow for the approximation of the centers of the powder grains so that densification can occur, with the final target of achieving a residual porosity equal to 0 or very, very close to it, very low. that is less than 0.5. For aesthetic purposes, 0.4, 0.3, bearing in mind the distribution of powders, because we're talking about an average value, which is measured in a certain area. But of course, the dimension of some pores could be different. There may not be homogeneity. So the mechanism, the two competing mechanisms in the debinding area, that is, the first part of the cycle at high temperature of the sintering process, derive from the fact that for some alloys, for some powders, the debinding process takes place at much lower temperatures compared to the beginning of powder aggregation. This is the case of AZ1316, where the necking temperature is 950 degrees, whereas the binder evacuation temperature, which lasts several hours and takes place at 400 degrees, is not competing against the first phase. For silver, these two mechanisms compete one against the other, because for silver, and this is our practical experience, necking starts much before the temperature of 400 degrees is achieved. So this prevents us from having a simple heat cycle without having to pay special attention to the different temperatures required. So this is a problem that still has to be totally resolved, and that requires, or could at least be supported, by specific binders for low temperatures. On top of that, there are windows of excellent sinterizability that depend on the nature of the alloy. In some cases, they're pretty wide. This is the case of steel. In other cases, they're very narrow, for bronze, for instance, for which the excellent sintering temperature window is very narrow, leading to undesirable results, so that in the lower part, I do not have a good sintering and no mechanical resistance. If I get very close to the solidus temperature, there is the risk of significant distortions. After curing and debinding, the true sintering process starts. That envisages specific atmosphere depending on the type of alloy, depending on the type of material. Sintering ovens that are compatible for MIM, where the binder content is still pretty significant when the item is placed in the oven, envisages the use of reducing atmospheres with partial or total pressure, hydrogen, or the possibility of insufflating during some parts of the cycle inertizing gas like nitrogen. For platinum, we have used an oven that uses air, since platinum has some highly desirable features, the very high temperature and the very strong oxygen inertia. Therefore, that high temperature allows me to work easily and eliminate the binder. Vacuum is not advised for sintering because it prevents heat homogeneity in the chamber, which is fundamental to guarantee that all items inside the chamber on the different trays are correctly treated, heat treated. This is the standard sintering cycle for stainless steel. We have phase 1, the binding, which has been extended significantly because of the shape of these items. This is similar to the cycle of microfusion with chalk. In the case of investment customing, we got wax. Here we got the binder, so it's a different thing. And then we have the curve that represents a sintering phase. And the phase of densification takes place in the upper part of the curve, so about 1400 degrees. If the item doesn't have any specific problems, the cooling curve can be the one that you can see here, and then fast cooling can continue. So the cycle usually has a duration of 23 hours for steel. It is a pretty long cycle. Therefore, we usually take into consideration 48 hours because the printing phase has a duration of 2 to 4 hours. Then we have the curing phase and the sintering phase that are usually carried out overnight and that are much more time-consuming. Finishing. The binder jet technique deposits powder, and we can generally check the process by analyzing cross-sections. This gives us an idea of how well the item has been produced. And this is the list of the materials that we have treated. The first one was steel, AISI 316, with excellent results. We believe that this now is mature, and it has a pretty wide sintering window. Powder granulometry, as initially suggested by the supplier. Well, this steel has the characteristics that are desired. The presence of nickel as such can be a limiting factor in some markets, but the softness and the mechanical resistance, which is not all that high, could actually play a role. We have also investigated steel panacea, which is a nickel-free, much harder steel used in fashion. It has been used, although it has very special characteristics in terms of the risk of obtaining, after sintering, the precipitation in a ferritic phase with very low electrochemical resistance and significant issues of corrosion, which would mean worsening the aesthetic characteristics. The sintered item can be treated to sort out the problem of corrosion, 1,100 degrees for 2 hours in nitrogen. But of course, this is costly because it has to be carried out in other companies. So we're now working on a treatment that then can take place during the sintering phase through the insufflation of nitrogen. And this has already significantly reduced the problem, although we cannot say that the result is excellent yet. We have also used a hard steel. It is a nickel-based steel, 17.4 pH. This has been our working bench for powders that have been produced with water atomization. There were no problem during the printing phase, with the exception of a more marked shrinkage on the Z plane, something we still have to sort out. Silver has been the first precious material we have worked on. So we started on the metal, because we're starting with sterling silver at the beginning, but the eutectic phase, which is marked in the binary alloy, represented a problem for densification. So this is why we changed the formulation to minimize the problem. And final residual porosity now is less than 1%. So in some cases, the result is much better than the 0.9 of residual porosity, but it still depends on the morphology of the item. So we still have to work on this alloy. We still have to fine-tune it to be able to say, yes, it perfectly meets the needs of the jewelry industry. Another example. This has been easy from the very beginning. Platinum 950. Since last October, we have started printing with this material, which is perfect from many viewpoints. Excellent heat resistance. The sintering phase does not cause any specific problems in terms of the heat level that needs to be reached. The debinding and necking temperatures are based on two mechanisms that are non-competitive. So from the very first printing experiment, we achieved a residual porosity less than 0.5%. So dense items have been obtained with a powder that was slightly coarser than described in the literature, which had 20 micron. So we can actually think about using this powder also to produce products to be sold on the market. So to conclude, steel and platinum high melting alloys can be viewed as mature to be used for jewelry, watches, and fashion. They're stable, functional, and they can be submitted to serial tests for later production of larger quantities with the MAME technology. So BJT is not an alternative to MAME, but the possibility of working without using a die of thousands and thousands of euro is a good advantage. The challenging side, however, is still related to alloys of gold and silver. For silver, we have made some progress, and this year we're going to study gold as well. We're going to investigate gold. So these are two aspects that will characterize our work in the new year. And our targets are making use of these powders with this technology and analyzing the technical features as we have done for the other alloys already. Thank you very much. I would like to thank the LEGO team, and thank you very much to all of you for your attention.